Good morning, all. Let me thank BMSIT, uh, all the organizers, especially Professor Gopinath. This is my second presentation here. I remember last year I had delivered a talk on instrumentation techniques in environmental engineering. And Dr. Ghorpade has been in constant touch with me. I know that to organize this type of events in this type of pandemic event, how difficult it is, especially when we are going through such a bad phase. FDPs organizing FDP is real a challenge. I appreciate all those people who are attending this. I believe you all are following lockdown. When they told me to speak, and when they asked me what I was going through your FDP title, and which says current trends in civil engineering, and it says 21. And when they asked me, basically, I'm not a civil engineer, I'm a chemical engineer. And then I did my all specialization in environmental engineering. So, how I can contribute in current trends in civil engineering? I was thinking about this. So I thought I'll speak about my area, which is in water and wastewater treatment, basically, and what are the trends, what people are doing outside, and for that matter, what problems we are facing in India. So I thought I will have a discussion on this. I'll be briefly sharing some of those research ideas or the things which are going on in field. We call them as superfund sites. Basically, was sites which are contaminated or polluted because of some other issue, and how they solve those things, and how environmental engineering, especially in water and wastewater, what the trend is and where the future could be. So I might not be directly contributing in terms of current trends of civil engineering, but definitely environmental engineering is a part of civil engineering. So I thought I'll speak on this topic. I can justify this particular topic. So I'll be sharing my presentation here, and might be some ongoing works if time permits. What we are doing in our lab, I'll be sharing that part also. And in between, if you have any doubt, questions, or you feel to discuss, please can stop me in between, or at the end of the presentation you can discuss with me. So I've given a title as recent trends in water and wastewater treatment technology. I believe in remediation part of it because a lot of work is already there, wherein data analysis is done, or we know what problems we are facing in water and wastewater. So I believe my entire research has been into how to solve some of those problems. So I worked on some organic pollutants, groundwater basically, and how to treat them, remediation technologies. So I'll be discussing those things. So if you look into this, I'll be discussing briefly about groundwater problems in India, different technologies to address the groundwater problems. There is something called PRBs, permeable reactive barriers, and this has been my area for some time. After coming back to India, I started working in this area to develop materials for remediation. Then the interesting part is cement-based solidification and stabilization, where cement is used to treat the pollutants, and how exactly it works. We have been working in modifying the properties of cement. Basically, as a civil engineers, you know that cement is construction material. But then I dealt with developing specialty cement, wherein that can be used for treating the pollutants. We worked on some mineralogy of the cements. When we study concrete technology, we know that there are some minerals like ettringite and monosulfate, and they have quite potential to solve some problems of water. On how exactly that works and how we develop some materials, I will be explaining you that. So if you look into this particular problem, we have a traditional problems in India in terms of groundwater. You can see fluoride is very common problem in India. Over exploitation of groundwater or naturally available salts of fluoride, they create a problem in water, especially the areas in Karnataka. Also, Ramdurg, Gadag districts are polluted with fluoride. Rajasthan is polluted with fluoride. I mean, groundwater is there. having high concentration of fluoride. Andhra Pradesh, you know, Nalgonda techniques, those who handle environmental engineering, Nalgonda technique, most of us, we know that. And this is a problem which is a very severe problem. Fluoride is there in the water, and lot of technologies have come. These days we speak of membrane technology and other things. Apart from that, there is something called arsenic, which is naturally present, or sometimes industrial effluents will create a problem. But arsenic is naturally present in soil in West Bengal, and people, the first photograph what you see where the palms are shown, those are of arsenic poisoning basically. The second photograph where you can see a skeletal fluorosis, where mid 40s lady got affected with the skeletal fluorosis. Basically, this fluoride affects the calcium part of the bone, and it leads to the permanent deformation of the bone. So these are all serious problems what we have. But these problems you might have heard from number of speakers, or you might have come across a lot of research in this area. I have a slide called East versus East. The reason is we always compare East versus West. But then I was in an Eastern country. I was in Korea for some time for my research. But I saw a big difference in research in terms of research development, what I would say, and where they are concentrating in water and wastewater treatment, which pollutants they are targeting, and where we stand in India, where we are treating water and wastewater to what level. So basically, we are still into macro pollutants. Basically, we are still into managing BOD, COD, solids of the wastewater, and probably we are still dealing with some other aspects of water. But wherein in an eastern country, already they have gone to the micro pollutants. That means some of those pollutants which we never heard about, they are working with those pollutants. Especially, for example, I would like to say in India, we use chlorine as a disinfectant for disinfecting the water. But now the research which I saw in 2009 in South Korea, they were studying the adverse effect of chlorination on human health. That means if you put chlorine, of course it is used for a disinfection, but then they are studying the adverse effect of chlorination. There is something called NDMA. It is called as a kind of complex organics, nitrosamine, basically, which gets generated because of chlorine combining with the organics of the water, and that is known to be a carcinogen. So if you put excess amount of chlorine in the water, how exactly it is going to adversely affect the human health? They are studying those type of problems. If you look into this photograph, you can see that there is an industrial pollutant.
Sorry to interrupt, sir. Sir, the slides are not changing, sir.
Slide? No, I have stopped it. Can you see the photograph now?
No, the photograph itself I am not able to see. That's
now?
why.
Now?
No, sir, you are in the first slide only. Yes, now it is. Now it can be seen.
Now you see?
Yes, sir. Yes.
Is it seen?
Yes, it can be seen.
Okay. Now, when you look into this type of problem of industrial waste, where industry is leaving its effluent into the water, we speak of ETPs, effluent treatment plants in industries, but it is always a questionable thing in India how well the ETPs are working. Or it could be as simple as some solvents which are used in paints, or some solvents which we regularly use, like typewriter correction ink, or some inks which are there in our regular printers, or for that matter as simple as kind of nail polish or nail polish removers what we use. You have thousands of chemicals which are there, and then these chemicals, if they enter water, what is likely to be there? So these are some of those very different categories of chemicals which we have not concentrated to treat in India, especially the water treatment plants in India, or for that matter wastewater treatment or effluent treatment plants in India. They really don't consider these type of pollutants. But then these pollutants are treated, and people are developing research, or you can say technology outside India to treat this type of, and that is the reason, one of the reason why cancer rate is going up. If you look into the statistics, cancer rate is really going up. The reason is environment is getting polluted with these micro pollutants, and which we are really not bothered about. The reason we are not aware of these pollutants actually. So that is the biggest problem. So for that matter, if you look into this photograph, can you see this, where the petrochemical tank is leaking. Okay, this photograph is seen. I mean, picture is seen. Hello.
Yes, sir. It can be seen, sir.
Okay, so by chance, if petrol leaks or some petrochemical products leaks, or what happens? So you can see that in this case, uh, these chemicals will go into the aquifer, and these are called as naples and denaples, non-aqueous phase liquids and dense non-aqueous phase liquids. They will not get mixed with water basically, but denaples, especially when they are heavier than water, they will go below the water and they will get accumulated in the on a soil surface, and whenever water passes through it, those chemicals will be carried with water. So there is a percolation of these chemicals inside the groundwater, and groundwater is kind of damaged permanently. I have seen some cases in India with the industrial pollution and industries. I will not name the industry, but some consultancy works had come to us, and then they were kind of worried because in and around that industry, the open wells were polluted, and they came up to us and saying that how to solve this particular problem. But if you ask me practically, it is very difficult to solve this type of problems when the chemical is associated with the soil particles and all the time the water is moving through it, because it depends on what type of chemicals they are. Remediating this type of sites is very challenging actually. So apart from our regular problems, there are specific problems what we are dealing with. Now, how they treat this type of water, groundwater. So basically, if you look into these technologies, there are a number of technologies these days which are in advanced research stage and execution stage, wherein that research which is done in laboratory is implemented in field already. So some technologies like pump and treat, wherein they'll remove the water, treat it, put it back. Soil vapor extraction, basically they heat the soil to remove the vapors. Basically that will create an atmospheric pollution, but then there is something called PRB, permeable reactive barriers. I'll explain you what exactly it is. Then there is phytoremediation. You might have heard that they plant some species which will absorb these pollutants. But of course, it is another questionable thing that mass transfer is happening, that pollutant is moving from ground into the plant species. What you will do with it ultimately. Then there is something called solidification and stabilization, which is with cement systems. I'll be dealing with these two, which has been my research area. So if you look into this, there is something called PRB, which is very popular technology in these westernized countries. So suppose there is a groundwater flow is there, and that flow is having some pollutants, and you want to treat this. So you know that this is a plume basically, which is polluted with some chemicals, and you want to treat this. So basically what they do is they study the groundwater hydrology, especially there are a number of factors which will be taken into consideration, and they will create this particular barrier across it. And this barrier which is created, this will have a material inside it which will treat this water. Okay, and whenever the water flows through this, it is
Sorry to interrupt you again, sir. Sir, sorry to interrupt you again. Again, the slides, they are stuck, sir. They are not changing.
Can you share it? I will share the slide with you.
Yes, yes, yes. That'd be fine, sir. I can do that.
Yeah, 1 minute.
Sir, you can do one thing. If you are in slideshow mode, you can exit from slideshow mode and then you can present.
I'm in slideshow mode, but then screen will not be seen with full this thing. Is it okay?
Yes, yes, that's fine. At
Now,
least
now,
that's
now you can
changing.
see it. Now you can
Yes,
see it.
yes, we are in the sixth slide now. Yes.
Okay. So if you look into this, basically the groundwater which is there, it is polluted with this plume is polluted, and whenever this plume moves through this particular barrier, you can see this barrier is called as permeable reactive barrier, and in this barrier they fill a material which is capable of treating the typical type of pollutant which is there in this particular groundwater. So ultimately when the water is moving through this particular barrier, it is, since it is permeable barrier, it will not obstruct the flow of that water. On the other side you will get treated water, and this entire story is happening below the ground. So probably if time permits, I'll show you the real time photographs also. There could be a playground on this or parking lot above this, and you will not realize that the water is being treated below your feet. Okay, so that is the level of treatment what they are thinking. uh, the quantity of the water which flows on surface, equal quantity of that water, in fact more than that water flows below the ground. And so when the groundwater gets polluted, it is very important that you have to treat that. So this type of technology is coming into this is a recent technology which people are using in those sites which are polluted with these pollutants. Now, my area of interest has been what type of material you should put into this, because there are number of different reactive materials. We call it as permeable reactive barriers. So there's a number of reactive materials depending upon what type of pollutant you have in the groundwater. So a huge area is opening up for the environmental engineers, wherein apart from traditional treatment, you have to come up with some materials which are capable of treating the pollutants, and those materials are engineered materials. A lot of material science will go into it, and if you come up with a good material which will treat this type of pollutants and which will have a field application, then there is a huge scope in terms of earning money also, as well as solving the societal problem also. So if you look into this, permeable reactive barriers, they are reactive materials which will be kept in subsurface, designed to intercept the contaminant plume basically, and whenever they are flowing through this, they will convert this into less harmful products. The pollutants will be converted into less harmful products, or they will be treated and they get transformed, which will be acceptable by the environment norms. So that is the meaning of PRBs. Now, this is the animation what I had put here. I told you what is LNAPL and DNAPL, light non-aqueous phase liquid and dense non-aqueous phase liquids. And whenever you might have come across some problems in India wherein petrochemicals leak into ocean, or some ship is carrying some oil tank and it leaks, or some petrol pump underground storage petrol tank leaks. Those are very serious problems, because if those chemicals which are there in those petrochemicals, they are so deadly chemicals, and treating them becomes almost impossible. Okay, so those type of pollution problems are really serious problems. So this is what is PRB basically. So if you look into this advantages of PRB, environmentally friendly technology, the materials what you're putting for treating the pollutants, they are eco-friendly technologies. So you're not going to spend on pumping or pulling out and pushing it down the groundwater. You are need not pull it out and push it down in the ground. So no energy involved in this. No waste generation or emission. Basically, the materials what you develop, you should make sure that the end products which come out of it are eco-friendly. It is not going to create any problem. Some of those materials like ZVI, zero valent ion, we call, they are used to treat chlorinated solvents. Chlorinated solvents basically come with chlorine attachment. So these days, a lot of chlorinated solvents are there. PCE, TCE is there, trichloroethylene is there, PCB, polychlorinated benzenes are there. A lot of chlorinated compounds, pesticides which come with chlorinated attachments, some dyes like azo dyes. If somebody is working on textile industry, and if you are coming across something like methylene blue that has a chlorine attachment, and they are known to be carcinogens. So especially when you want to break that bond between chlorine and that compound, you require some electron donation mechanism, and zero valent ions are known for that particular thing. So they usually use these ZVIs for treating TCE, PCE, and this chemistry is well established chemistry. So basically ZVI chemistry is well established chemistry. So if you look into this, zero valent ion is basically the valency of the ion is zero. In first reaction, you can see that valency is zero. And further, when the ion gets oxidized to ferrous form, it gives 2 electrons. If it is in ferric form, it will give 3 electrons. Now, these 2 electrons are used by that chlorinated compound. RCl, what you see is a chlorinated compound like trichloroethylene or perchloroethylene. And because of that electron donation mechanism, it will be broken. Now you can see that it is giving out chlorine. So chlorine is coming out, and this is a kind of electrochemical reaction which happens with materials. So ultimately, when there is an electron donor in a system, that electron, these are called as redox reactions. We call it as oxidation and reduction reactions. And these type of reactions are common with the microbes also. So you might have heard about a groundwater being treated or a soil being treated with microorganisms. So the mechanism remains same, electron donation and accepting mechanism. Okay, so this is the basic fundamental behind that particular reaction. Now, these are number of other chemicals which can be treated using PRBs. methanes are there, ethanes, ethylenes, propanes, aromatic compounds. These all can be treated using PRBs. Yeah, Egbote sir, slides are seen, right?
Yes, sir. It can be seen.
Okay. Now, if you look into this, there are different types of PRBs. First type is called as funnel and gate PRB. Basically, the groundwater flow will be there, and you can see there is a funnel here. This funnel is meant to regulate and direct the groundwater. It should flow through this particular reactive gate. So that is the reason why this is called as funnel and gate. So it will converge the water flow into that, and it will force that water to flow through that PRB. So that is how it is called as funnel and gate. You can see that continuous trench method is that they will put a trench and make PRB in that and allow groundwater to flow through it. So this is another method by which it is done. So you can see some of the combinations are there. So you can see plume of the reactive plume is there, and this is a reactive cell. So how this funnel and gate works and other combinations work. So basically, this type of combinations are made in a such a way that water will flow through those PRBs. They calculate the residence and a contact time, how much contact time that water will get with the material. So of course, for that all you need to carry out a lot of lab experiments. So we go in a lab scale first, then pilot scale, and then field scale. This is being implemented. I worked on one of those projects wherein I ended up developing a specialty cement for PRBs, or you can say not PRB exactly, grouting systems. We call it a cement grouting systems. So for the application in field, okay, you can see in field this is how it looks. PRB sites, you can see that they make a PRB in a first photograph. You can see this is how the construction will be done, and they put some material. In this case, they are putting zero valent ion in this. Basically, this is highly reactive material for those chlorinated compounds, and a lot of civil engineering work is required for this. Civil engineers' help is required along with environmental engineering specialization, and they put it in a trench, and then they will cover it from the top, and then groundwater will start flowing in this particular thing. So the active materials requirement, what you should have, it have high containment attenuation process. It should have contaminant attenuation process. Good selectivity should be there. What you are using, I mean, the material which you are using for PRB should be very appropriate. If I am using chlorinated compound treatment, then you should go for something like ZVI. But now if you are having some problems like nitrates, sulfates, fluoride, if this type of anions are high in concentration, then we go for ionic singeing materials like something like cement. Cement is known for ionic singe. So I will show you the detailed research what we did. Then it should have very fast reaction rates, reaction kinetics, what we call calculate in terms of K value. That reaction kinetics should be very fast. It should have good hydraulic permeability. It should not block the flow of the water. It will create some other problem otherwise. And long-term stability will be there, should be there. That means it should not immediately react, and that material should not get exhausted. ZVIs face that particular problem because they will get oxidized into higher state of iron, and their reactivity will be lost. So these days people are working on an area where they are working on a longevity of the ZVI. Longevity is basically they will control the reaction rates, at the same time oxidation rates of iron will be controlled by some protective layers. So they are working on that type of material. Okay, then it should have environmental compatibility. It should be acceptable by environment. One part of treatment technology is very important, that you treat the water and you should not create some other problem. That means you solve one problem of the environmental issue or water problem and then create another problem, then it is going to create a problem. Okay, so sufficiently available in terms of homogeneous quantity, that material should be available in good quantity, and cost effectiveness, that is another interesting thing. So those people who are from geotech background, I would like to stress on these things. You might have heard about clay-based liners in landfill systems. So if you look into the details of clay-based liners in landfill systems, solid waste landfill systems, again the chemistry goes with ionic singe and adsorption techniques. So you have different types of clay. We have worked on some clays like Montmorillite and bentonite clays, and we studied their properties at microscopic level, structural level, how exactly ionic singe and other things happen in that. So it's quite interesting that you have naturally available materials. These days we are working on chromium, hexavalent chromium reduction using lateritic systems, laterite which is available. and laterite has huge concentration of alumina and iron in it, and that iron has a capacity to reduce the hexavalent chromium, which is very dangerous to trivalent chromium. Now when we look into all this type of problems, and there is a material naturally available in a system, there is something called river bank filtration technique, RBF, and this is ongoing work in Tungabhadra river basin, where RBF is basically meant where the natural water from the river is flowing, and on the banks of the river they drill borewell or wells, and the water when it flows on in those wells, naturally that water will get filtered through the soil strata which is present, and that soil strata has a capacity to treat some of those pollutants. And if it is not, then you can engineer that particular system by introducing some materials which are capable of treating it. For example, if you look into seawater incrustation problems in the coastal region, seawater in Karnataka, in our own state, we have some problems in Karwar, this type of districts where coastal zones are there. The seawater get mixed with the fresh water, and especially in this belt of Karwar, Goa, you have lateritic zones, and then we need to understand the soil chemistry, exactly how laterite works. So this is very interesting study in terms of materials when we speak of these materials. Now, if you understand the reactivity of these materials for different pollutant system, same materials can be used in PRBs also, permeable reactive barriers also. So this is how exactly it goes. Now, laboratory skill studies, I told you should do lab skill studies before, and you should get concentration of that what concentrations the contaminant has, and then what pollutant, what rate it is going to degrade. You need to find the K values of it, groundwater flow rate, how it is there, that you need to determine. Then you have to calculate the residence time, thickness calculations for that particular PRB, and you need to find out all those things. Okay, this is how the column test can be done after in the lab. You have to maintain a column, then sampling ports are there, you can see, and as you move in a distance, the concentrations of pollutants are likely to change. So this type of column studies you can do after batch experiments. You can go to column study, and you can design a PRB for this matter. Okay, so you can see that PRB installation technologies are already available in field. Why I'm stressing on this type of problems is what we learn in environmental engineering from syllabus point of view is slightly I would say, of course basics are there in syllabus, but then we need to really understand what is happening on field, and then might be at least we need to make students aware of this technology, so that job opportunities, what you see slowly it is coming to India also. I believe that in few years, I'm really optimistic about this type of technologies, that this type of things will come to India also after few years. And by that time, we should be ready for this. So the technologies, what I'm discussing with you is my exposure from 2009 onwards. So you can say around 10, 12 years technology, last 10 to 12 years technology, what I'm showing you here. Okay. So this is extended backhoe, which is used to remove the soil. Okay, it can go up to 100 feet deep. Okay, and you can see that hydraulic camshell is there, and basically it will dig up to 150 feet inside. So these are some of those technologies which is used. This is used for you have to put the media which I was discussing, reactive media. When you want to put it into deep ground, you can use this type of primitive. Basically, this is deep mixing, soil mixing device, which can be the reactive material can be mixed with the soil and make it homogeneous in a composition. That type you can use this type of thing. So all these things, what I'm showing you are the machineries which are used, or technologies which are used to solve soil as well as groundwater pollution problems. Okay, so this is getting equipment, especially this is used when you're grouting a cement inside the ground. So cement grouting systems, we use this. Cement will go and sit on that pollutant, and that cement solidifies, and once the cement solidifies, it will not allow that pollutant to move, escape. That is what is called as solidification. What do you mean by stabilization? Cement will start reacting with the pollutant, and basically once it starts reacting with the pollutant, it will convert it into less harmful product. That is what is called as stabilization, and that is why it is called as SS technology, solidification and stabilization. So this is how that cement basically works. So they make a slurry of the cement, and they grout it inside the groundwater, and that there the cement will go and sit on the pollutants which are adhered to the soil particles, and that will start treating that particular thing. You need a good jetting equipment. You can see this. This is a jet which is used to put it in cement along with the cement slurry inside the ground. So this is how it is used. Now, this is a case study. I have put it here. Newport South landfill, basically US-based systems and other places they are using this. So composition of PRB, you can look into this component is you are having sand and gypsum. Gypsum is calcium sulfate, iron, and then hydromagnesite is there. So if you look into calcium, magnesium, iron, and silica combination is there. In this, everything has its own role. So silica helps in removing barium. Calcium sulfate also helps in removing barium. Iron helps to sorbing the zinc, and magnesium, manganese. It will help you to remove the manganese part of it. Magnesium will remove manganese part of it. This combinations has to be worked out in a lab. So basically, we are dealing with this type of issues. Now you can see that this is how the ZVI is mixed. Zero valent ion is mixed. Okay, and these are the chemicals which are mixed before it is put in trench. Basically, these are all reactive materials. Now this will be mixed, and this will be delivered on site, and it will be filled in those trenches, PRB trenches. This is a trenching machine which will create that trench. You can see this is a PRB. This is where they put this material, and then they will check the performance of PRB on a regular basis. So you can see that initial concentration in ppb. We speak of ppm, they speak of ppb, parts per billion level. Zinc from 100 to 1000, it has come less than 9. Barium has come. This is how they treat the groundwater. Okay, what I would say is, this type of technologies also will have its limitations. I'm not telling that these are perfect technology or something, but then this is a different way of treating the pollutants. We never thought that this type of technologies will be available. And when we are speaking that there is something called initial concentrations in PPBs, they are speaking at very lower level of concentration of pollutants, which is already affecting the groundwater, which has already affected the groundwater in this westernized countries. Even after taking care, even after they had wastewater treatment plants, ETPs, everything is there, but still their groundwater is having this type of problem. So I'm sure that in India, the conditions. So I'm sure that the day when we come across this type of problems, we require good engineers to solve this type of problems. That's the reason why this environmental remediation companies are really blooming up like anything. There are some very good companies which are operative in India also. Something like Atkins Global, they are doing wonderful work in environmental engineering in India also. Okay, so this is cement-based stabilization technology, where cement is used on these Superfund sites. You can say that sites which are polluted. Okay, so I told you how exactly cement works. Now here onwards, our research starts exactly what we have done. So if you look into this hydration, this is a very common cement hydration diagram, which you will see it in most of this concrete technology book. This I have taken it from HFW Taylor, which is cement chemistry book. You know that calcium silicate hydrate gets formed over a period of time, and then there are some minerals like ettringite and monosulfate, which are going to get formed in the cement. We call it as AFT, trisulfate, and AFM, monosulfate. Basically, ettringite and monosulfate are part of cement hydration, and these minerals will get formed when calcium sulfate in the cement, gypsum reacts with some phases like alide, belite, aluminate, and ferrite phase is what we call. So aluminate phase is like tricalcium aluminate phase. When it reacts with this basically gypsum, it will generate these phases like ettringite and monosulfate. And these ettringite and monosulfate have excellent property of exchanging ion. Now you see these are sulfate based phases. AFT is nothing but trisulfate. AFM is nothing but monosulfate. So this sulfate has, these minerals have a capacity to release this sulfate and take some other pollutant inside. For example, if you have a groundwater polluted with arsenic, and if I have this ettringite and monosulfate rich in the concentration, when I grout the cement inside the ground, then a sulfate will go out and it will take up the arsenic. so it will fix the arsenic. So I don't mind sulfate releasing it to, of course sulfate also has its problem, but then it is less dangerous compared to arsenic. So this is what is ion exchange technique. This is how we ended up making first patent out of it, wherein arsenic treatment was given using modified cement. Okay, so likewise there are number of applications, number of anions can be exchanged, like sulfate, nitrate, fluoride, phosphates, chromium also can be, of course it is a different mechanism, but then this ion exchange can be dealt with using this type of minerals which are getting generated during the hydration of the cement. So basically our research dealt with uh, modifying the cement properties in a such a way that these minerals will get generated more in quantity in a cement hydration. So in normal cement hydration process, these minerals will be having a limited quantity. So if you modify the properties of a cement, that cement is not used for construction, but of course we are using it for treating the pollutants. So there is a requirement of this type of specialty cements in the field, where you have this type of minerals which will uh, help us to reduce the pollutants. So the basic research deals with understanding mineral properties, what mineral is responsible and how exactly it works. So along, iron is also there in the cement, so it goes in a different direction, a redox reaction. Iron also can work as a redox material, along with that ion exchange. Especially some sites which are contaminated with the pollutants, and you are going for a site remediation, there is a requirement where they want a material which will treat, and it is eco-friendly material. So cement, I don't think it will create any other problem, because it is rich in calcium and silica, which is a part of nature, apart from the sulfate, which is in small concentration. So what we did was, we ended up designing different type of cement, which will give more of this ettringite and monosulfate. So I'm not going into the details of the chemistry of this, basically how we made it and all, but you can find a lot of literature in this, and you can see how exactly this mechanism is there. Everything is explained here. I'll not get into details of this, but you can see that we ended up designing some material, basically. Something like ettringite, you can see a SCM image. This has a hexagonal shape basically, and this has a capacity to exchange sulfate. Now you can see EDAX on one side and XRD on one side. We ended up designing aluminum ettringite and iron ettringite, something like that. Similarly, you can see monosulfate, which is having a hexagonal plate structure, and this is called as LDH. It is called as layer double hydroxide. It is something like a sandwich. You have two slices of bread, and then in between there is a vegetable which is stuffed. Something like sulfate is there, or along with hydroxide, sulfate is there in between layer, and that sulfate can go out, and fluoride can come inside, or arsenic can come inside, and we call it as layer double hydroxide. So we successfully we synthesize this type of materials in lab, on a, not from cement system, but pure minerals we could synthesize by synthesizing tricalcium aluminate first in lab, pure tricalcium aluminate, which is aluminate phase of the cement. Then we allowed it to react with the calcium sulfate, and we generated this type of minerals. And now you take this powder and put it in a arsenic contaminated water or arsenic polluted water. It has wonderful capacity. With few grams of that powder has a capacity to treat arsenic. So this is how it is. And then of course my professor already was into this area of research. He had published in good journals. They had done column studies and other things, what I was explaining you. I ended up developing or designing different types of cements, like cement depending upon its properties. So there are different types. We know, all of us, we know that there is something called ordinary Portland cement, OPC. These days getting OPC is difficult, because most of these cements are blended with pozzolanic material. So we call as pozzolana blended cements. Getting pure OPC is difficult these days, actually. You know that it is blended with fly ash and other pozzolanic material. So we get pozzolana blended cement these days. Apart from that, you can see there are a number of cements, like calcium aluminate cement. Calcium aluminate cement comes in variety. Calcium aluminate cement, which comes in alumina rich cement. Basically this is used for quick setting cement, what we call, because sulfate concentrations in this will be very less, and we call it as white cement also, because iron concentration also will be less in this. And then calcium aluminate cement, there are two categories. One is aluminate rich cement, and another is iron rich cement. Iron rich cement comes in gray color, because Basically, the color which comes to the cement is because of iron concentration in this. And then you can see a fourth category called calcium sulfoaluminate cement. So this type of cement, which is very rich in sulfate, I told you, if the sulfate is high in concentration, then that can be used to generate those minerals like ettringite and monosulfate. So especially this cement is called as expanding cement. If ettringite mineral is more in the cement, then ettringite occupies more space, and hexagonal shape of that rod will be bigger, and it occupies more volume. And that is one of the reason why you get cracks in your cement, because of high sulfate concentration. We call it a sulfate attack in concrete technology. But of course, it has applications also. Sometimes you require this type of cement to treat groundwater as well as soil. So why I'm showing you this is these cements are made on a commercial level. The reason there is huge demand for this type of cements for the environmental application. So that is the reason why it is shown here. So we ended up designing different types of cement. You can see this is oxide composition. We checked its reactivity. We found out which mineral is responsible for that, and then we saw some of those cements are not reactive for our pollutant which we were working on, trichloroethylene or something. We were working on those pollutants. They were not reactive, but however, we found calcium sulfoaluminates are excellent in treating some pollutants which are chlorinated pollutants. And you can see we established a kinetics for that. We found out how exactly it reacts, what is the reaction time required for that, and all those things. So these all things were done in lab. We ended up giving the results in K values, how exactly it reacts. We did combination of OPC and different cements, and we gave those pseudo-kinetics along with all these combinations. This is another example where you can see that K values are plotted with this calcium sulfoaluminate cement, and we found the best combination which can be used to treat the pollutant. Okay, and that combination we ended up giving in field, actually, where trichloroethylene plume was seen, and they grouted this type of cement in the field. Basically, we did a lot of mineralogical studies, and you can see that the cements which were reactive, you can see this peak of E which is there. This is there only in those cements which reacted, and we isolated that particular mineral which is responsible for treating that particular pollutant. And we came to a conclusion that ettringite plays a very significant role in treating the chlorinated compounds. And to prove that, we did XRD analysis, SEM analysis. You can see that figure C, you can see a rod-like structure here, which is of ettringite, which we found this is the mineral responsible. Then we designed the cement categories in a such a way that these rods will get formed in more quantity. You can see that flaky structures, plate-like structures are of monosulfate, and rod-like structure is of ettringite. So we did this type of research, and we got quite a good publications out of it. Very few publications initially. What we got was in some journals like desalination and water treatment. We found out. Then there are a number of other publications are not put here. Probably slideshow it is not showing. But what I'm saying you is, people asked me when I came back from Korea to India. They said that this research is there in Korea. What about Indian system? How can you do these things here in India? But I'm really optimistic person. I started working from 2014 onwards, and my entire MTech research group works on this type of ideas. And there are a number of papers in a review right now, but very recently we published a work in one of those ESCI's Emerging Science Citation Index Web of Science journal. And this data is purely from my MTech student here in Belgaum. So I have a hope that yes, we can do good research here in India also. Only thing is we need to diversify the research area, and we have to go into something which is really happening in field rather than following traditional treatment technologies. So that's what I would like to say. And yeah, hope is the last thing person can leave. That is what I always believe. India is a country where magic can happen. People have willpower to do many things here in India. There's a small cutting of the paper Hindu. I got this. Here in Rajasthan's Bharatpur district, they had the self-help is the best help they case. The residents they dig 1 kilometer long canal to lay cement pipeline. They said they did not take any help. And you must be knowing Nana Patekar is doing excellent work in Maharashtra, and they did not take a single paisa from government of Maharashtra. But then they constructed a canal for that drought affected areas. So I believe that research in India might not be everybody's cup of tea because of lot of difficulties. But I always believe that if you have a willpower and many things can be achieved. So with this note, I will stop my presentation. I hope I have done justice to this topic. We are going through a bad phase of pandemic. I request all of you to personally take care of you and yourself. Please follow all the norms, social distancing, wear mask, and stay safe. Thank you. So I will leave the session open for discussion. If you have any doubts, you can ask. I just went through the slides. I don't know how much you have followed in that, because if we have to speak in detail about those materials and all, it requires a lot of time, might be series of lectures. So this was an overview of recent trends. What I felt, one of those areas where we ended up designing some materials for treatment of very specific pollutants. So yeah, I hope I have justified the title of that talk. Thank you so much. I thanks BMSIT for giving me this opportunity. I thank you all for listening to me. Thank you. Thank you so much. Yeah.
Thank you, sir. It was very much thought-provoking and extensive research that you have done. As you said, really, sir, we are looking forward to have a series of lectures on this, because
Yeah.
these kinds of topics are really that we are expecting in our present society, because we are dealing with lots of contaminated water. So we need water treatment and such kind of technologies that you spoke just now. So these however, we need to bring up in present days.
Yes, sir.
Yes, yes. And as sir said, now the discussion is open for a question is, I would like to invite participants to have discussion session. Do we have any questions here? Sir, we have a question here. How can we motivate civil engineering students to work on environmental chemistry oriented approach with limited time and opportunities? Wish to know if your lab is willing to support such research.
Yes. See, basically, as I told you, most of us, the basic problem, I don't take me in other way, but the basic problem in Indian engineering system is we don't learn basic science subjects. So if you look into environmental engineering, there's a lot of chemistry involved, and I don't know, till PUC second year we study chemistry, but afterwards we don't study chemistry. There is a big gap between the basic science people and engineering people. I saw this gap is not there in foreign universities. I mean, engineers chemistry is equally strong when they are dealing with this type of problems. Even when I went outside, my chemistry was not, still it is not that strong. But then what I believe is, when we are teaching environmental students or probably engineering students, especially civil engineering students, when we are teaching, they get scared of chemistry. So first thing, as a teacher, what we should do is we should teach them chemistry, which is application chemistry. You don't just put a reaction and show them that this is a reaction, you by heart the reaction or balance this reaction. They get scared of balancing reaction, or they will not really understand why that reaction goes like that. So I believe that physics, chemistry, and mathematics, these are three subjects which have to be taught from application point of view. That is where it is really missing. I always feel that. So I do handle some of the chemistry classes here in my MTech PG program. When I am teaching aquatic chemistry to them, I deal with subjects like water treatment technology. But water treatment technology will not be purely engineering class for my students. So I start with basic chemistry, because unless they understand basic chemistry, they will not understand the application of it. So motivating the students in limited time is really big challenge. But those who are running a PG program or those who are running a UG program, we have started a unique concept in our MTech environmental program. Sapna Upadhyay is here. She is my student actually. She can justify that. When we do these projects, basically. Especially 2 years program, MTech PG program, we do project batches at the end of first semester only. So we don't allow those project batches. I mean, we don't do them at the in the last semester where they are supposed to do in last 6 months. We don't do that. We have changed this slightly in a of course unofficially. I would say official batches we make it at first semester end, and then what I do is I put those students with my senior students to work in the lab. and then they will continue the work. And then what we do is we are working on one single project for, I mean, senior works on that project and junior will carry forward that work. Senior will come to some level and stop it there, and he'll submit his thesis and get going with the degree, but the junior will continue that work. What happens by doing this is the chemistry becomes very clear. The reason that junior is exposed to that problem for at least 3 semesters, and we are continuously discussing that chemistry. So what happens is they will develop a lot of interest in the field of chemistry and aquatic chemistry. This is the change what I have seen in few years when we tried doing these experiments in our small group of students. So it all depends how much exposure of chemistry you are going to give to them, and how you are motivating students to solve the real life problem using chemistry. I believe that chemistry has a solution for everything, but we as engineers, we fail to apply chemistry. We get scared of chemistry basically, and especially environmental problems. If our chemistry is strong, I believe that most of the problems can be solved. So yeah, motivating students by showing them something which can be used in terms of application, and you teach them how exactly that chemistry works, definitely it will click. There are beautiful books written by some authors like Sawyer and McCarthy, which is, I believe it's a bible for environmental students. Okay, so these days students are not reading books, they are all with their cell phones, but it becomes very difficult to motivate this type of students generation. Then we also have to change our approach. I always believe that. I don't blame them for using mobile phones, but then we have to teach them something which they will understand in their own language. So I have been experimenting quite a things, and they are working. You can see that we are doing Web of Science or SCI publications with MTech students data. It takes little time, but yeah, I'm still optimistic it is possible. Yeah, it can be done. Yeah, any other question? Hello?
Any other questions?
Hello?
Yeah, Dr. Mahesh, you can say, sir, if you have any question.
Sir, good morning. Good morning.
Good morning, sir. Good morning, Mahesh, sir. Yeah.
Yes, sir. This is, sir, first of all, I would like to tell you that this is very nice session.
Thank you, sir.
Really, if possible, sir, request will be that you share the PPT, because this is really useful to us for the teaching community.
Yes, sir.
And
Yes,
yes, that is my request. And one more thing is that, especially, sir, when if you see the students, those who are carrying out the final year projects, mostly
yes, sir.
students, they are carrying out the projects in the structural area or concrete area.
Yeah.
It is necessary to motivate them.
Yes, sir.
So my question is that, so in which area, sir, we should take the students to perform their projects, or is it possible to give some themes so that I can motivate the students to work in this particular area?
Okay. I understand the problems of students are universally same. Since I am working in civil department, most of them, they will think that if you do project in the structural area, they are having better job opportunities or something. I'll tell you one issue I discussed with my colleagues also who are in structural domain. See, what happens is, let them do project in any area. The way in which we are doing the project is very important. I will tell you how it is. I'm one of my research group is working on making clay bricks. We are making clay bricks in geopolymeric area, and the works what we are carrying out is purely, I would say, civil engineering hardcore work. But then I'm not pushing in an area where they conventionally work. Like, you take some 30% of fly ash and you mix it in that, and then you change the concrete design, or modify the mixed design, and you end up adding some things, and randomly you come up with I mean, I'm not telling that that results are not right or something, but we are traditionally trained in such a way that go on adding 5%, 10%, 20%, and get the compressive strength, split tensile strength, and all those things, or flexural strength and other things, and document and finish it off. But what happens, see, why it is happening like that, or if you are proving that with addition of 10% of something, what reactions are happening inside it. If structural students also, if they take up in that domain also, there is a huge work which can be done. I showed in my presentation, my entire work has been in cement chemistry and analyzing the minerals which are going to get generated. Now, why don't structural engineering students start thinking in this area where they are mixing something to make concrete strong, and then what exactly it is happening inside the concrete and why the strength is increasing. I don't believe in physically blending the materials and getting the strength. Of course, that is required at one stage, that you need to prove that by physical blending you can do. But then a cement is an area, or a concrete is an area which is very complex system. People end up using fly ash, silica fume, and blast furnace slag, and mixture of all these things. First of all, cement itself is a complicated material. I showed you the complication of that in terms of environmental part, how ion exchange and other things could happen. Then taking a small module in a structural part and going into deeper level at microscopic level or a structural level, it will be worth learning for the students. So they end up learning some instrumentation, some analytical tools, some statistical tools with their project. And it will, if it's a blend of all these things, the project will come out as a beautiful learning tool. Otherwise, what happens is they will do traditional project and forget it. It might not help their in their career. I till date get interactions from my students whom I had help in structural engineering. They were not my students actually, but for analysis of XRD, FTIR, or for that matter, semidax analysis or any other analysis, like now we are dealing with XPS analysis and other things. They say that, yes, sir, what you had told, it is used in industry these days. And we are really this thing that we want some help from you to analyze some samples from industry orient. So what I believe is when you're giving a project, let's not think from submission or report point of view only. Let's get into the details of that work. We have to create lot of interest among the students. And I have seen once we ignite them, definitely they'll come up with some work. So I always believe that I will not give them target that you have to finish the project on so and so date. No, it is, of course, for UG it is a limitation. I understand that, but then you motivate them in a such a way that whatever results come, positive, negative, how to interpret them and solve them, it is possible. So I believe there is one more area where structural and environmental people can work together. You know that reinforcement corrosion problems are there, or chloride attack is there, sulfate attack is there, or you have bacterial concrete. You have so many areas where jointly a multidisciplinary knowledge is required to work. So you club projects like that where people have a diversified interest, guides have diversified interest. Why I'm telling you this is when you think of publication and other things, this really helps. With pure strength part or pure mixing part, or for that matter, even in environmental part also, by just reducing BOD or COD, you cannot come out with good publications. So you require sophisticated instrument, and since you people are staying in Bangalore, you have exposure to good institutes from where you can get all this analysis done. So I believe the project should be designed in a such a way. Preferably, you take some live projects from industry where they are having a problem. Don't promise them that you will solve their problem, but at least you get a problem statement from them and start working on it for some years. Definitely, I believe that all of us, we have a capability to at least contribute some solution to the industry. So I always take up a project which are challenging, a small module from the industrial problem, and we try to work on it and try to solve it. By doing this, we will help students also. We will also learn along with them. That is what I have practiced. So it's a good practice. That means if you take industrial project, small problem from an industry and try to solve it, I believe that is worth doing. And the projects will also gain a lot of importance. And students also will appreciate because they are working on live problems. So design of the problems when you are giving them projects, I don't believe in searching it on internet for the problem. There's a lot of problems in and around us. So if we approach them, I believe those can be solved. So we can have a separate discussion on this. I will show you a number of projects which we are doing here in Belgaum. So sir, definitely I will be very happy if sometime I will leave my email address and other things. We can communicate sometime. If you want to involve students also, we can involve students also for the discussion. Yeah. One thing what we have maintained here in KLE is we keep labs open for them. I mean, especially in PG program, I don't believe in lab timings and other things. So I keep lab opens for my PG program, and all the time you see that my PG students will be there in the lab. Entire freedom is given to them to work in the lab, provided they are supposed to use all the equipments carefully. So they take that responsibility. When we show them trust, they will also show that trust. I have seen this change. Yes, it is possible. Yeah.
Thank you, sir. Thank you very much.
Thank you, sir.
Wonderful information given.
Yes.
And really, I would like to pass on my faculties as well. Actually,
Yes,
I am living in a very remote area.
Yes, sir.
In Eastern Karanji. and
Oh,
working as a head of the civil engineering department.
wonderful,
So
sir.
really nice information given, and I will pass to my faculty.
Please, please, sir. I'll be very happy to interact sometime with students also.
Sure,
If
sir,
you come
sure.
down to Belgaum, do visit our college.
Sure,
We can
sir,
have
sure.
interactions, sir.
Sure. And
Yes.
thank you to organizers for giving me opportunity to interact with you. Thank you very much, sir. Okay.
Thank you.
Do we have any other questions? I think we don't have any more questions, sir.
Yes, sir.
Uh, okay. So, sir, I would like to, sir, there is one more question. One
Yeah.
more question come up. What are the new areas in combination of structural and environmental?
Okay. Uh, See, these days we speak of specialty materials, concrete also, as well as in environmental area also. Now, especially, I was telling you just now, we need to explore some material parts in concrete, basically. Now, already we know that a lot of things. See, I'll tell you one simple example. What we are dealing, I'll not explain everything. It's an industrial issue, actually. They mix red mud in cement. I don't know whether you are aware of this or not. I mean, red mud is generated in huge quantity in alumina industry, and they are not understanding what to do with it. And they blend some part of red mud in cement. Actually, since cement has iron oxide, Fe2O3, so red mud has huge concentration, around 43 to 45% of red mud has iron in that. Now, industry comes up with a typical problem. They say that if we put red mud beyond one particular percentage, it is affecting our strength of the cement. Now, see, this is a real challenge from industry. They want us to tell to what level we can blend the red mud. Blend in the sense at the manufacturing end, when you're pushing red mud in the kiln end, manufacturing end in the sense feed end, when the raw material is going inside the kiln at the feed end, if I put red mud, what is going to happen? They want us to know the phase transformations which are happening, or whether your four phases which are there in the cement, allied, belite, aluminate, and ferrite, whether those phases are going to get affected or whether strength will get affected. Ultimate part is the cement has to be kind of marketed. Tomorrow, if you put something in that and if it affects the cement quality in an adverse manner, then it is not going to help. Incidentally, fly ash has found very good application in the cement since it is having wonderful pozzolanic property. Now, see, there is a typical problem wherein they want to push something like red mud in a cement, and then they will ask for a help from civil engineering faculty from both structural as well as environment domain, because this is an environment concern. Red mud disposal is an environment concern, and associated problem with the red muds are purely environment concern. Now, when I put this in a cement, it becomes more complicated, where a lot of environmental and cement chemistry has to be studied. And now structural engineers role come, wherein you make some concrete out of it or strength part of it and how exactly it works. So now you see there is a beautiful combination wherein structural engineering student has to work on its all strength related issues or mixed design part of it. Environmental engineering students have to work on the chemistry and environmental chemistry and a cement chemistry of it. And then you club these two domain knowledges to come up with a strong evidence or strong results out of it, which will be fit from both the sides. What is happening is environmental students or environmental faculty, we are not good in your concrete part, and concrete people are not good in chemistry part or materials part. This is where it is failing. So you are going in one direction, we are going in another direction. So this is where you can come. And I'm giving you just one example. I told you another example. Reinforcement gets corroded over a period of time, but we study electrochemistry of iron corrosion, and a few years back, we had a project wherein there was a chemical which is available in market which will prevent corrosion of iron. I was telling you during my presentation, zero valent iron is coated with some chemicals to prolong its oxidation reaction. Now you see that we learn it in PRB materials, but can I apply it in concrete? Because your reinforcement over a period of time should not get corroded. Now, why this corrosion happens? It is sulfate attack, it is chloride attack, or it is alkali reactions, or whatever it is. Now you see, when you want to prevent this type of a problem where this reinforcement corrosion happens, there was a typical case which came to us from fertilizer industry where reinforcement was getting again and again corroded because of ammonia exposure there in the fertilizer industry. Now they come up with a typical problem saying that you give us a mixed design or give us some solution so that this concrete or reinforcement will not get corroded. Now, can we solve this problem? This is another area where structural engineering and environmental engineering have to work together to come up with a solution. Now, the chemical which is used for inhibiting the growth of or inhibiting the rate of reaction of corrosion, that can be developed by environmental people. I mean, there is a lot of environmental chemistry involved in that. You understand how this sulfate attack is there, chloride attack is there, and prove it. And the other side, you have to design and take help of structural engineering. So domain wise, there are huge different areas in which it will work. Now you see, we are working on a foundry sand, basically a waste foundry sand in Belgaum. And now if I put this foundry sand, whether this foundry sand is a physical filler or whether it is going to chemically react in a concrete, how many of us we know that? We put sand, yes, but then there are 4 different zones of sand what you use in a mixture, okay? But now this sand what you're physically blending in a concrete, whether it is really going to react or whether it is physically going to go and fill the space, that we don't know. We have not proved it. So this is another combination where problem of environment is there with the foundry, and a lot of people are working on how to utilize this waste foundry sand, and structural people are there. Physically you will blend it, I know that many people are doing 10%, 20%. What is exactly happening from that? Because this sand which you are blending might have some chemicals attached to it in a foundry, how those chemicals react and all. So this is a part. Then how the leachate characters will be there. This is the environment part, how it will affect if something comes out of it. What is that? What are those chemicals which are from environment point of view which are dangerous, and how it is going to react in a concrete part. So what I'm saying in a broad term is there are a number of areas where we can concentrate and bring these 2 different domain knowledge. It's not only structural engineering and environmental engineering. You can club number of different disciplines. We ended up doing image processing, taking help of electronic people for one of the industrial wastewater problem. We were solving some problem of algae, but we felt that we should take help of image processing, and we ended up using image processing in wastewater treatment problem. So problems will be verified, I mean diversified, and then how to club them and bring it to a common point is really interesting. So I believe that people from different domains should sit together first, and then we should be open to exchange the knowledge. What is happening is structural person will work with his structural expertise, environment person will work with his environmental expertise, and then this is where it is not getting bridged. So different knowledge people should sit together and then contribute, open for the discussion. I don't mind sharing all my research, but then how many of us we discuss research? That is where it is a big hitch. And then some person is associated with something, his students will be working with him, they will not interact with other students. This is where it goes in a different direction. Probably now in our department, we have started working in materials area. We analyze XRD, SCM. These have become very quite common practice, irrespective of which domain they are using these tools. So we should start like that. I believe that we can do this. There are multiple ways in which 2 domains can be clubbed, not only structural, number of other domains also. Yeah. Anup sir. Hello.
Thank you, Praveen sir, for sharing your deep insights. I'm the faculty from Department of Civil Engineering, Nitya Meenakshi Institute of Technology. I have asked this question. Mahesh Kumar.
Mahesh sir. Thank you, Mahesh sir. Thank you. Thank you so much.
Thank you, sir, for your nice presentation also. Thank you.
Thank you. Thank you.
It was awesome.
Thank you. Yeah. Ekbote sir. Hello.
Hello, sir. Am I audible now?
Yes, sir. Yes, sir.
Sorry for that interruption, sir. My network went off. So,
no. Yeah.
Okay. So I think we don't have any more questions.
Yes, sir.
And Sir, I express my deep gratitude, sir, so that you accepted our invitation and you presented your research and you shared your research with us. And
Thank
we are looking forward for future collaboration with you, sir.
Yes, sir. I'll be very happy. It's my pleasure to be with you all to share whatever knowledge I have. I thank all faculty who have attended this, especially faculty from BMSIT and the organizers of this FDP. Congratulations for organizing this, and stay safe and maintain distance. Take care of yourself and your family. Thank you so much.
Thank you.